Hello everyone, welcome to my channel and welcome to this video. So this video I'm once again going to start with a question. Let's say you have a server-side program or a server-side application where you want to listen for incoming connections using sockets, right? In such an application, apart from the business logic, the first thing that you would want to do is set up your listening sockets, right? Set up your listening socket. It can be TCP, it can be UDP, but you need a listening socket which will accept connections on a particular IP or all IPs on the server, basically all interfaces on the server and a particular port. Once the socket has been created, you put it on listening mode, you call the accept system call on the socket to accept connections, to accept the client socket, and then you read from the socket and write to the socket and whatnot, right? So now let's say you have such a daemon process or a daemon server which accepts connections and serves requests. One of the issues with this is that doesn't matter when the first connection is made to the server server application and the business logic will always be running on your system, right? If it's a daemon which gets fired up on system boot, it will keep running in your system from the very start of the system, whenever the system comes online, whenever your machine comes online. And that's to some extent a waste of resources. For example, what I'm trying to say is that let's say you have a server-side program which gets very sparse requests, right? It doesn't need to be up all the time. It gets requests once in a while, let's say, but it gets very important requests, but those are less in number. The traffic is less. Let's say the first request, it might come at a way later point in time, but when you are bringing up your server, you need to make sure that the daemon comes up so that when the request comes, it's able to serve it, right? And not to mention, like with such servers which are supposed to be highly available, like it's supposed to be running all the time, changing the server program or updating the server program is always a hassle, because the moment you take down the program, the listening socket goes away, right? The listening socket goes away, and it means there is chances of connection drop. And then once again, very quickly, you would have to respond the server. Well, there are certain ways to mitigate this, right? We have discussed in one of my previous videos how SODU port can help this, and you can have multiple instances of the server program listening on the same port and things like that. But again, this is always a problem, like hitless reload or hot reloads, right? So now my question is, how can you handle the case where you don't need the server process, the heavyweight server process running all the time, even if there are no requests, right? Or even if when the first request comes at a much later point of time, right? How can you do that? So the bottom line question is, can you make your system receive connection without the actual server program being up, right? Is that at all possible? It sounds a bit weird and illogical, but that's what we are trying to achieve. We want the system to accept our connection somehow, right? There needs to be some listening socket somewhere in the system which accepts our connection, it keeps the connection with that socket, and then it spawns an instance of an application and passes this connection to that particular server program. That's what we are trying to achieve here. We are trying to spawn the server on demand when there is a connection, so that it's not running all the time and wasting our resources. So that's a very interesting problem if you think. Like usually in traditional programming, for example, what we do is usually we start the server then and there, right? So that is ready to take connections. So what we are talking about is decoupling the listening socket from an actual server-side program. So if we can do this, if there is a entity, if somehow that entity is able to accept the connections on that particular listening socket, we have decoupled the listening socket from the server-side program, which means if for a split second the server program goes down and a new instance comes up, the connection is still received and is passed on to the new instance of the program. So that also to some extent will solve our problem of hitless reloads. It would provide us, like in theory, it would provide us with another way of fixing the hitless reload problem, right? So let's see how we can achieve this. And very interestingly, in Linux, there is one such tool that can help us do this, that can help us decouple the listening socket from the actual server program. It can spin up the server program. It can spin up an instance of the server program on demand when it receives the first connection, and it can also help us with hitless reload. And that entity or that tool is nothing but our very own systemd, which is right now the de facto init process, like PID1 process for most of the Linux distributions. It's also the daemon manager on most of the Linux distros by default, right? Let's see how we can achieve these things. So as always, without further delay, let's get started. Okay, so to understand how this works or how this enables us to do the decoupling of the socket and the program, and how it can help us to perform hitless or hot reloads, we need to understand certain things. So although I have mentioned it multiple times in my past videos, but I'll just quickly go over it once again. So whenever you are creating a typical server-side program for networking purpose, like which can receive and serve requests or any peer-to-peer connections, what you would want to usually do for, let's say, for TCP is, although it works pretty similar to to UDP. It's just that for UDP you do not need to establish a connection beforehand. You can simply send out your packet, your datagram. But for TCP, I'll just consider TCP here. So for the server side, what you usually do is you create a socket. You mention that it's the type of the socket, like mostly something like AF inet. It will be a sock stream, and like the default option for sock stream, for example TCP. And then you put it on, you call the listen system call. You provide a queue, right, which like basically the number of concurrent connections it can receive and store it in buffer, which is very, very important, especially in this case. Then you call the accept system call on this socket. If this socket is S, then you call it on S, and you also provide a buffer for client socket, client sock, right? And then also somewhere before the listening call, which I just missed, somewhere over here, you would also want to do a bind, and here you would pass the address as well. The address would pretty much be a like sock ADDR address. It's something like sock ADDR star address that you would bind your socket to. Usually for a AF inet type TCP socket, it will be something like a IP and a port, or basically ADDR any, IF ADDR any and a port, right? Which means now that socket is bound to that interface, and it's listening for new connections, right? And then it's pretty much your business logic where you can read on the client socket, store things in a buffer, you perform your business logic, and then you write back. Yeah, you write back something to your client socket, right? That's what you would typically do. Now, the problem why we need to always keep our server running from the very first instance, whether we have or we do not have a new connection, is because of this, is because of this part, right? Is because of this part, and to some extent the accept call as well. But the most essential part why we need to keep the server program running from the very first instance, irrespective of any incoming connection, is the socket creation part. Because usually when we develop a server side programs, a socket program, we do the listening socket creation and bind also as part of that particular program, which is not always necessary, right? Like, I mean, it has got nothing to do with your business logic. The creation of the socket and the binding of the socket and putting it on listening mode has got nothing to do with your business logic. The actual importance of the listening socket for the business logic comes into picture when the socket is already ready, right? It's able to accept connections, and you just put the accept syscall on it and get the client socket and do a bunch of things with it. So if somehow we could remove this part from the program, if somehow we could remove this part from the server side program, let some other entity manage this creation of socket for us, right? And then when the first connection comes on that particular socket, and how can you understand if there is a connection on that particular socket? A number of ways can be there, right? You can that particular entity who is managing the creation of this socket, that can do something like a iNotify or epoll. It can also do epoll to understand, to get notified when there is a new connection, like we did in one of our previous epoll video. There are a number of ways by which that particular, let's call it a socket manager, that socket manager entity can find out if a new connection has arrived on this socket. And the moment a new connection arrives on its socket, what that system, that daemon manager or that socket manager or whatever it is, that entity can do is basically it can fork and exec a new instance of our server program. Let's say this is our server program now, which doesn't care about the socket creation, and this is a socket creation which happens in our daemon manager / socket manager, right? So the moment the daemon manager finds out that a new connection has arrived on the socket that it's managing, it knows which program or which server side program this connection should go to, and what it can do is simply fork and exec an instance of that server side program, and it can pass that listening socket. A listening socket is nothing but an FD, right? It passes that FD to that particular program. It can pass it as a argument when it executes it. It can pass it as an environment variable, or it can pass it via some other shared library call, right? It can also do that. So there are a number of ways where you can also pass it to that program. So You see, like Linux has taken care of all these things already for us. It's just that instrumenting these things end to end. And in past, there have been certain daemon managers which have tried to do this. For example, inetd is one such example where it would, for every incoming connection, it would spawn an instance of your server-side program, which is again to some extent a wastage of resource because you are spawning multiple instances of the same program. But point is, in past, people have indeed thought about this problem, and people have done it using inetd and other stuff as well. So something similar was recently done. Not recently, I mean it has been a decade, I believe, since it came into picture. So systemd, along with the multitude of features that systemd provides as a init1 process, daemon manager, and so many things, it also gives you this option of decoupling socket and activating a service only when there is or activating a daemon only when a new connection has been received on its decoupled socket. And this feature provided by systemd is called socket activation. It activates your service on receiving a connection on the socket, and hence it's called systemd socket activation. So systemd provides allows us to manage the socket separately, right? And it also allows us to register a daemon service with systemd, and systemd somehow maintains a mapping between which socket belongs to which server program, and whenever the first connection arrives on that particular socket that it's managing for that program, it will spawn an instance of the program, right? Now the question here is, like, we do not have a backing service, but we are accepting the connection on a separate program who is managing this socket. So there will be some time gap, right, between the time when the connection arrives at the systemd maintained socket, or let's call it systemd socket, and the time systemd takes to spawn the new service. So what happens to the connection in between? How does that work out? And by the way, systemd does not only provide stream socket, it also allows you to configure UDP socket, Unix domain sockets, netlink sockets, and whatnot, right? It has provisions for almost all types of sockets. So the question is, what happens to the connection metadata or the incoming connection during the tiny amount of time, when the connection arrives at the systemd managed socket and when systemd spawns the actual server program? So turns out during that point of time, the kernel buffer or the kernel socket buffer stores the connection metadata for you. So the moment, so let's say we have got the sys socket or systemd socket for short, and we have got the server program, right? And here is some client, and it makes a connection, a TCP connection here, right? And the server program is not up yet. So what happens to this socket? Like, it works in the pretty usual way. What happens is that this connection is stored in the kernel socket buffer. Also, in short, it's known as the SKB or the socket buffer, right? The kernel has a buffer to store these socket connections. In short, it's called the SKB data structure or the kernel socket buffer, and your data stays or your connection metadata stays there. And the moment the server program is up, systemd will pass the socket FD to this server program along with the connection, the first connection, and then for future cases, the server program can call the accept system call on the socket FD, and it can continue with its work, right? So here the fundamental feature of like this storing this connection is already being provided by the kernel using its kernel socket buffers, and systemd is just making use of it in a very nice and smart way to do this systemd socket activation feature, right? Just one thing we need to note here is that, so let's say the client is booting, and when the client is booting, it needs to create a connection to some other server program already running on the same server. Let's say this client is also a server process, and this server process is dependent on some other server process on the server in order for this client's booting, right? Now if the client is only interested in making a connection or sending a Unix domain packet to this server program, and it can now simply do it. Like, it doesn't have to, this client is no more blocked on this server program to actually spin up for the client's boot up itself, because now it doesn't really care if the server program is up or not. It can simply create the connection with the systemd socket, or it can simply send the UDP packet or the Unix domain socket packet to the systemd managed socket, and the client can think, okay, the service on which I'm dependent is up, and the client can continue with its booting. Which brings us to a very interesting point about synchronous and parallel booting of system processes when your system is booting up. So let's have a look at that, how this helps us with that. Okay, so let's say when your system is booting up, so we all know that when your system boots up, when the init process comes online, it spawns a number of processes, right, which are required for the normal functioning of your system. Things like your various daemons, your network manager, your syslog, your Bluetooth manager, and all those various things that starts up when your system comes online. So all those things starts one by one, and oftentimes there are dependencies between them. For example, your Bluetooth manager or your network manager might be dependent on your syslog, because the moment it comes online, your network manager comes online, it might want to log something into your system logs, for which it might use syslog, right? The syslog device file, and that injects certain dependencies and blocking situations in the entire process of bringing your system up. So to simplify this thing, what I'm trying to say is that, let's say there is a process PA, PB, PC, and PD, right? So let's say PB depends on PA, right? So PB needs PA to boot up first, and how is it communicating with PA? Let's say PB is communicating with PA via some Unix domain TCP socket or Unix domain stream socket, right? For now, let's call it PB is communicating with PA over Unix domain socket. So the expectation is the moment PA comes up, PA also creates the Unix domain socket with it, puts the Unix domain socket on listening mode, and PB should be able to communicate with PA on that listening socket. And the first thing that PB would want to do is send some packet to PA, and only then PB's boot process can continue, right? And let's say there is PC, which is dependent on PB. So once PB comes up, its Unix domain socket comes up, PC now can contact that socket, establish some connection on, maybe it wants some ACK, and it can continue with its boot. And let's say there is another process called PE, and now let's say PE is both PE and PD is dependent on PC. So now what essentially it means is that both PE and PD needs to wait for PC, but both of these can happen in parallel. Both PE and PD can boot up in parallel, but both of them needs to make sure that PC is first up, so that it can contact its PC's Unix socket or some socket to send some data or create a connection or something like that, right? As I already mentioned, the requirement might be different from process to process. PB, it might just want to create a connection with PA. That's it. It doesn't want to do anything with its boot process, not send a packet or anything else. PC, for example, maybe it needs to send a packet to PB and get back a response for PC's boot process to continue with. And PE and PD might again just want to make sure that maybe the domain socket is simply available. It doesn't even want to perhaps make a connection. It simply wants to make sure that the domain socket is just available before they can continue with their boot process, right? So these can be the different requirements. And with the traditional sysv init or system 5 init, whatever you call it, it was the admin's job to define these relationships, right? Like PB can start only after PA has come up, PC can start only after PP has come up, and PE and PD can start only after PC has come up. So in a way, PA, PE and PD can start only after PA has come up, and so on and so forth, right? Now just imagine how socket decoupling can help us, right? So what system D would do in this case is, and what you can actually do with system D also, you can define these relationships. By the way, with system D you can define targets, and you can also define wanted by. There is a clause in system called wanted by, using which you can define which service is wanted by which service for its boot process and things like that. So you can always define such relationships with system D as well. But the other thing you can do with system D socket is that if these processes support system D socket activation, or if you are able to patch these services to add support for system D socket activation, then all you can do is you can decouple PA's socket to SA. So this is the system D managed socket for PA. For this we have SB, we have SC, and for this we have SE and SD. So now basically what happens is that even if PA is not up, system D has already created a socket for a Unix domain socket for PA, right, which is extremely fast, and PA can take its sweet time to come up. Now when PB comes up, PB sees that it can create a connection with this SA, right, or it can send a packet to SA. Now if PB just wanted to create a connection with PA's socket in order for its boot process to complete, it sees that it can create a connection with SA, and SA is present, so now PB can continue with its boot process, right? And if PB can continue with its boot process, PC can boot up faster. Even for PC, it doesn't even really matter if PB is up or not, right? PC can see that SB is up. Now PC can see that SB is up, and the domain socket file is present. So PC can also continue with its boot process. It doesn't have to PC doesn't have to block on SB anymore. And similarly, PE and PD knows that SC is up now and it can create its connection with SC. PE and PD can also continue. So what I'm trying to say is that now you do not care about that relationship. Systemd is managing that relationship for you completely, and it has abstracted the entire thing. So in a way, you are starting all the processes parallelly, and the systemd can add the sync between them using the systemd socket activation feature. So now all the processes get spawned parallelly and they are not blocked on anything. So only time it can block is like when, for example, PB, there is SA and there is SB. So PB has sent a packet, it needs to send a packet to or some data to PA, and it needs some data in return. Only that time PB might block because PA is not up and the connection goes to SA or the data goes to SA. The data is with the kernel socket buffer, right? Only when PA comes up, it can pass that socket, listening socket to PA, and PA can receive that data and sends back some reply. But again, even for that, you do not have to care about the relationship at your end. This is all being managed by systemd. And worst case, PB simply waits for PA. It doesn't crash or anything because PA is not accepting connections. Because systemd socket is accepting connections, it's storing it in the kernel socket buffer, and PB can simply wait. So the entire this relationship configuration is shifted from user domain to the systemd domain, and systemd manages everything for you, right? So that's a huge advantage that systemd provides us, and it speeds up the boot process end to end when you compare it to sysvnit. Okay, so now that we know what is systemd socket activation and to some extent how it works and how we can use it, let's see it in action. So in this video, I'm going to show how we can use systemd socket activation in our socket program written in C. I won't dig much into systemd because that would take another couple of videos in itself, because systemd is so much sophisticated and it provides so many options and features. But I would only focus on the kind of unit files we need for this to work and how we need to modify any existing socket program or network application in order to use systemd socket activation, right? So yeah, let's see how we can do that. So here we have a very simple socket application. It's a simple echo server. Like it first creates a socket, then it assigns it a listening address. Like I'm using inaddr_any. Its type is AFINET. The socket address is, as I mentioned, is inaddr_any, which means it would listen to all interfaces, and for port I have designated 55555, like 5 5s. And then I am simply binding it. I am listening, putting a queue size of 10. Then in the infinite loop I am accepting connections. I am reading from the connection, and then I am simply whatever I am reading from the connection from the client socket or from the accepted socket, I am just putting it back into the into the client socket FD so that the client receives the same thing, right? So that's a simple echo server. So for client, once again, I have a simple bash script where I am just in a loop from 1 to 100. I'm simply making TCP connection calls and sending some data, like something like echo hyphen the index number and a prefix, right? And I'm sending this to 127.0.0.15555 as a message, as a TCP packet, and whatever I'm receiving back, I'm simply printing it, and I'm doing it 100 times using NC netcat. Okay, so far so good. Let's compile it once, although I just compiled it a while back, but still I'll do it once again. So I'll do a gcc-o server.c. I'll just divide my terminal into 2 halves. Okay, so now let's start the program which we just compiled. Okay, so our server is now waiting for clients, and let's start our script. I mean, we can also, for this purpose, we can also do direct netcat. So yeah, it's a simple echo client, as I mentioned. Okay, so what we are now going to do is we are now going to add support for a systemd activated socket, or rather systemd managed socket. And for that, what we have to do is we no more need to initialize this socket. Rather, we can initialize this socket as a fallback when we do not receive a socket from systemd, so that if no socket is passed on by systemd, we can spawn our own socket. So that way our program will be resilient enough that even if it doesn't get any socket from systemd, still it would be able to accept connections. So the first thing we would want to do is start with a new include statement, and we are going to include systemd daemon.h, sd-daemon.h. Once we have included this, we'll get access to a few systemd specific function calls. We could have also accessed this listener socket passed from systemd via environment variables, but I'm just going with this systemd function call for now. I'll just remove this sleep for now. So now what I'm pretty much going to do is I'm going to check if systemd has passed on any socket for me, and I'm going to do that using sd listen fd. So this is the function that comes from this sd-daemon.h file. The next thing that I'm going to do is I'm going to check if n is greater than 1. So remember, like what I'm going to do is I'm going to create one systemd managed socket for this particular program. So I should not be getting more than one systemd managed socket. So if I get more than one, I'll simply log that. More than one socket fd found, and I'll perhaps exit it. That's it. Else if n equal to 1, which means we have actually got a systemd managed socket, and for that what I'll do is I'll store it in sockfd. Sockfd is nothing but a int variable where we would store the socket fd, and I'm going to use a macro called sd listen fd start, and again once again I'll log it. Got socket fd using this fd, and I'm simply going to print it. I mean, I'll just print the value of the macro because I know this is the fd that will be designated for the socket fd. Okay, so it would be a good time to mention about what is this sd listen fd start, and or what is the offset from which the socket, the file descriptors for systemd sockets, systemd managed socket starts. So usually every process would have three standard descriptors, file descriptors open, right? These would be, I already have created a video on this in past about file descriptor, file descriptions, and all those things. So the three standard file descriptors would be 0 for standard input, 1 for standard output, and 2 for standard error. So any number of file descriptors designated for systemd activated sockets that's passed to this program would start from an offset of 3, because 3 would be an unused fd in this case for this process. So again, you can have multiple systemd managed sockets for a given process. You will just have to mention those in your systemd socket configuration. But yeah, so if we just check the value of this macro, it will be 3. So the first passed descriptor is fd3. There is a reason why it says the first passed file descriptor and not just socket file descriptor, because with systemd you can not only have activated sockets, or rather systemd managed sockets, but you could always also have systemd managed FIFO queues and whatnot. Those kind of things you can also have. So that's why it just says file descriptor, and in Linux pretty much everything is a file, so you would need file descriptors for it. So now we have got hold of our socket file descriptor passed from systemd, and what do we do in else part? What if nothing has passed? So we fall back on our usual manual process, not manual but our usual process. So in the else part, I would simply move this entire code, right, and I will end the else block. So if nothing is passed, then we create our own socket in the traditional way. We bind it, we listen for it, and that's it. And that's pretty much it. So now what we are going to do is we are going to create our unit files to configure our systemd managed socket and the systemd service itself. So we will convert this server into a daemon, and in order to do that, so we'll call this server program echo, and the first thing I'll create is a echo.socket. Okay, first I would create, let's create let's create echo.service first, because that's a daemon thing which we would need. So it will be a very simple systemd service type unit file, and it will be exec start /home / pretty much my home. So it will be pretty much /home / actually I don't need to do it from my mind. I can simply do this, and I will simply copy this, put it here, and do a server which is the binary that I just compiled. See, I'm not mentioning any systemd targets over here, like multi-user.target and those kind of things, because I'm not going to do a systemd enable on this, right? I don't want this service to be started at the system boot time when the multi-user.target becomes active for systemd. So in systemd, corresponding to every sysv run levels, like we have a corresponding systemd target. Multi-user.target would roughly correspond to the run level 3 when your system is ready for a multi-user environment. So if I would have mentioned here a multi-user.target configuration, what it would do is, if I do a systemd enable systemctl enable echo, it would copy this configuration to the multi-user.target module of systemd configuration, and or rather multi-user.target directory of systemd configuration, and that would essentially mean whenever the system comes up, next time I boot my machine and the kernel hits the systemd multi-user target, my server would spin up, which I don't want, right? I want it to be activated by the systemd socket. So it will be a simple echo.service file, and the next thing I'm going to do is I'm going to create the echo.socket file, and the name needs to be same, or else you would have to explicitly mention in your service using wanted by. So we don't want to do that for now. I don't want to do that, and hence I'm just keeping the name same, and it's a pretty decent way to do that. And keeping the name same sounds good because this socket is meant for this service, right? This socket configuration is meant for this service. And what I'm now going to do is I'm going to create a tiny socket configuration. So the name of this unit will be socket. So I am using a stream socket, hence the listen stream parameter I am using, and the address would be a IPv4 address along with port, so 0.0.0.0 because I want to listen on all interfaces, same as IDDRNE, and the port and the target port, which is 55555. And finally, although I won't be using this, but still I would do a install. So when I want this to be activated, or when I want this to be created, in case I want to auto activate or auto create this socket or auto start this socket, so I'll simply do a wanted by equal to sockets.target. So that's when I want this socket configuration to be activated, when the sockets.target systemd target is reached, right? Okay, that's that. So now we have got the socket file and the service file created. All we need to do now is copy them. So I'll do a sudo cp and echo.service to etc system d system, right? We are going to copy this to etc system d system, and I'm also going to copy the socket file as well, right? And finally, what I'm going to do is I'm going to start the socket. So right now, if I do so first I also need to do a systemctl daemon reload. This will just reload all the unit files, so that systemd knows that a new echo service and echo socket has been created. So now if I do a systemctl status echo.socket, we'll see that it's there, but is inactive, so we need to make it active. So for that, we'll do a systemctl. So before that, if I do a nc, I won't be able to connect, right? Because our server is not running. Also, since I added the systemd support, I also need to recompile my server. So for that, let's try to do that. And it failed. It failed because we need to link it to the systemd library, right? So we need to use that. We need to mention the systemd library while compiling it using the -l switch. So let's do that. And it worked. Okay, so that's that. Now let's start our socket. We could have also enabled it. It would put it into the correct correct systemd target, but for now let's just do a sudo systemctl start echo.socket, and now let's check its status. It is running. However, if we check the status of echo echo dot service. It's inactive, right? It's inactive, but it mentions that it is triggered by echo dot socket. So all we need to do now is send some data, and it should get activated. So let's see if it works. Let's try to do once again our NC 55555, and let's see what happens. Did it start? And it started. Our echo service is up, but we didn't spin it up manually. All I had to do was create a new connection to the systemd socket, and it spun up the server program, which is the echo server. And let's now try sending some data, and I'm getting back. It's working perfectly fine, because the moment the first connection arrived at the systemd managed socket, which is echo dot socket, it knew which service that echo dot socket was meant for, and it immediately activated that particular service, that is echo dot service, brought up an instance of it, and passed the connection to that particular server or particular server program. So yeah, it works now. So now what I can do is, once again, I'll simply stop this service. Actually, let's start our client program now. So it's sending packets once again, and now if I do a sudo systemctl stop echo dot service, what happens? It works fine. And why does it work fine? See, there is no discontinuity in what we are getting. We just stopped the service. If I see it again, it's working. It's still up, because the moment the next connection was made after I stopped the server, the systemd socket got that connection, and immediately it started the server back up. And that's the beauty of systemd activated service or systemd socket activation. Okay, so now we know how we can use systemd socket activation to spin up a server instance on demand. And let systemd socket handle the first connection. Let's see how we can update our program on the fly without losing any packets or losing any data. So once again, my server is running now. Let's make sure that it's running. Let's make sure it's running. Echo dot service, it's up. And now let's start the loop. It's running. I'll open it up. I'll open it, and what I'll do is I'll simply do a, let's say I'll do a strcat. The destination buffer is puff. I will add a simply I'll add something random. I'll just say test, or let's say something like echo test \n, and yeah, that's pretty much it. And I believe it will be puff. And since I added 1 2 3 4 5 6 7 8 9 plus 1, since I added 3, since I am now sending a few more characters, I'll just update the size as well. So it's size plus 10. And why is it still? Oh, okay. Okay, so now all I need to do is recompile, and I'll do a systemctl stop echo dot service. And look at that. The moment I stopped, the immediate next connection it once again started the server back up, and the updated version of the server came online, and I'm getting the updated messages, which just prints a echo test after the first line, right? So using this, I can also, as I just mentioned, using this I can also do a hitless reload, right, without dropping any requests. However, if we are using this method for performing a hitless reload, we also need to keep in mind that existing connections to the server, where we are doing the systemctl stop echo dot service, or maybe systemctl dot restart echo dot service, whatever we are doing, we need to make sure that we gracefully terminate the existing connections that's already present with the server socket. And the reason we can be sure that there is no connection drop, because since the socket is now decoupled from the program, when we take down the program, we are not taking down the server socket, the listening socket. The listening socket is still up with systemd, and it will use the kernel socket buffer to store the connection metadata it will give some time to the actual server program to come up, the new server program to come up, right? Perhaps what we can also do is try to, try to simulate some load. Let's add a sleep 10 over here. Let's add a sleep 10 over here, and remember it's a connection oriented socket time. That is, there is a stream socket. When the echo packet is being sent, that will be a blocking call. But the effect that we are trying to look forward to is that no connection should fail. The client side should block, but the client side should not return us an error, or it should not be a packet drop, right? That should not happen. So let's see if we can achieve that. So now what we have done is we are simulating some delay in the next instance of the server coming up. When we'll be trying to spin up or when systemd will try to spin up the server, there will be some simulated delay. And let's see if the client fails or it faces an connection error. So we'll we just compile it once again, and let's just do a systemctl stop echo dot service. Now it's stopped, but the socket is still up. So let's try running our loop once again. It will start creating the connections once again. Okay, so now the server is taking some time to come up, but see, we haven't faced any connection error yet. Yep, and the 10-second delay is done, and we are receiving back our responses once again, right? So now what I'll do is I'll simply once again update the server program, and this time I'll just do a -2, right? I'll just add a -2, which means it's now 1 2 3 4. So I'll just increase it by 4, and let's once again recompile our code, and once again I'll stop echo.service. Now look at that. Since it's TCP connection, it's blocking. The client is blocking, but the client has not failed, right? The client has not failed yet. It's simply blocking. And check this out. Once the delay was over, the 10-second delay was over, it once again started receiving responses, and this time updated response, because our server is now updated without losing a single request, right? So that's another way of performing hitless reload using systemd activated sockets. So yeah, that's a pretty cool feature that's provided by systemd, along with the various other multitude of features systemd provides. So yeah, that's it for this video. I just wanted to I found this feature really cool of systemd socket activation. I have known about this for some time now, and I really find it interesting. So I wanted to make this video showing this entire feature and how it works and how we can use it, how we can patch any existing server program to add support for systemd activated socket, and how we can create a systemd socket for our service and start using it straight away. So yeah, that's it for this video, and let me know in the comment section if you all have also used what features of systemd you have used, right? Have you used systemd managed sockets? Have you used systemd managed FIFO or systemd managed mount point? What all you have used from the systemd suite of features. So yeah, that's it for this video, and hope you all enjoyed this video, and see you all soon.